Relational Tuple Storage Engine. Overview and Architecture. The Relational Tuple Storage Engine, or RTSE, is a persistent columnar storage system designed for moderate-scale analytical workloads. The engine organizes data into fixed-width tuples arranged in contiguous memory blocks called segments. Each segment maintains metadata describing column type definitions, null bitmap offsets, and compression codec selections. Segments are addressed through a global segment identifier, which encodes shard assignment and logical ordering information. Column encoding and compression. Column encoding operates independently on each attribute within a segment. Supported codecs include run-length encoding for low-cardinality domains, frame of reference delta compression for numeric sequences, and dictionary encoding for string attributes with high repetition. The codec selection occurs during segment finalization, guided by cardinality statistics computed during the write phase. Codec metadata is written to the segment header alongside column offset tables. Null bitmap construction and traversal. Null values are represented through a per-column bitmap with 1 bit allocated per tuple slot. The bitmap is constructed during column write operations and stored in a dedicated section of the segment. Bitmap entries are packed contiguously without alignment padding. During tuple reconstruction, null checks perform bitwise and operations against the corresponding bit position, returning 0 for null values, and a positive integer otherwise. Segment lifecycle and rotation policy. Segments transition through 4 states: open, sealed, committed, and archived. The open state permits write operations and memory allocation. Once a segment reaches its configured size threshold or maximum age, it transitions to sealed state, preventing further writes. Committed segments undergo durability verification and are registered with the Global Segment Catalog. Archived segments are eligible for garbage collection after a retention period specified in the engine configuration. Write path and tuple serialization. Write operations append tuples to the current open segment without modification. Tuples are serialized according to the schema type definitions for that segment, with fixed width fields written inline and variable width fields stored in an auxiliary heap area. Each tuple receives a logical sequence number that defines its order within the segment. The sequence number serves as the primary tuple identifier within segment scope. Read path and predicate evaluation. Read operations specify a set of target segments and optional filter predicates. The engine scans each segment sequentially, evaluating predicates against tuple attributes in column major order for improved cache locality. Predicate evaluation halts at the first false condition for conjunctive predicates. Results are accumulated in an output buffer of configurable capacity, triggering a flush once the buffer threshold is reached. Index structure. B-tree organization. Segments may maintain optional B-tree indexes over specified columns. The B-tree implementation uses fixed node sizes aligned to the system page size, typically 4 kilobytes. Internal nodes store key ranges and child pointers. Leaf nodes contain key value pairs mapping indexed values to tuple offsets within the segment. The tree maintains balance through standard splitting and merge-in operations triggered during insertion and deletion. Index lookup and range queries. Range queries traverse the B-tree from the root, following child pointers until reaching leaf nodes. The traversal performs binary search within each node to locate the target key or the predecessor key for range starts. Queries with open-ended ranges perform linear leaf node scans from the starting position. Index lookups return tuple offsets, which are then used to retrieve full tuples from the segment heap. Concurrency control, reader-writer locking. Concurrent access to segments uses reader-writer locks, permitting multiple concurrent readers or a single exclusive writer. The lock implementation uses a reference counter and a single binary flag indicating writer status. Read operations increment the counter. Write operations wait until the counter reaches 0 before acquiring the flag. Lock acquisition follows a fairness protocol that alternates between pending readers and writers. Transaction isolation level. Snapshot isolation. The engine implements snapshot isolation through timestamping. Each transaction receives an increasing transaction identifier upon initiation. Read operations see segments and indexes with timestamps less than or equal to the transaction identifier. Write operations serialize through a global write lock, ensuring total order among committed writes. Aborted transactions release their locks without persisting changes. Garbage collection, segment reclamation. Archived segments become eligible for garbage collection once their retention period expires and no active transactions reference their identifiers. The garbage collector marks segments for deletion and removes references from the global segment catalog. Disk space is reclaimed through OS file truncation or deallocation calls. The collector runs asynchronously and does not block read or write operations. Memory allocation and buffer pool management. The engine maintains a configurable buffer pool for caching segments and index nodes. Allocation uses a LRU eviction policy with explicit pinning support for high-priority segments. The buffer pool tracks dirty pages and coordinates with the durability layer to ensure written pages are flushed before eviction. Pool utilization statistics are exposed through a metrics interface. Durability and write-ahead logging. All mutations are recorded in a sequential write-ahead log before segment modifications occur. Log entries contain the transaction identifier, segment identifier, and delta information. Periodically, a checkpoint operation records the current consistent state, allowing the log to discard earlier entries. Recovery proceeds from the most recent checkpoint, replaying log entries until the failure point. Catalog and metadata management. The engine maintains a metadata catalog describing all tables, segments, indexes, and their configuration parameters. The catalog is versioned through atomic modifications and persisted in the write-ahead log. Schema changes acquire exclusive locks on affected tables and complete through a multi-step process recording the change type, affected columns, and new constraints. Query optimization and execution planning. The query optimizer accepts SQL parsed into an abstract syntax tree and generates execution plans through cost estimation. The optimizer considers segment statistics including cardinality, null ratios, and value distribution. Plan candidates include sequential scans, index-based lookups, and nested loop joins. The optimizer selects the candidate with the lowest estimated cost. Configuration parameters and tuning. The engine exposes configuration parameters for segment size, buffer pool capacity, write-ahead log batch size, and garbage collection intervals. Parameters are specified in a YAML configuration file and loaded during initialization. Most parameters cannot be changed after engine startup without reinitialization. Performance tuning typically involves adjusting segment size to balance memory pressure against index effectiveness.